To commemorate this International Year of Astronomy, 3 of NASA's flagship observatories have put a new spin on how we see the Pinwheel Galaxy.
You might be hearing a little more buzz about astronomy these days. That's because the International Astronomical Union and UNESCO have designated 2009 to be the International Year of Astronomy. What's the occasion? This marks the 400th anniversary of looking at that with one of these. In 1609, Galileo first turned a telescope towards the heavens and began reporting things that would forever change the way we view the universe.
To commemorate the anniversary of this new way of seeing the sky, NASA's great observatories have teamed up to give us a whole new way of seeing the famous Pinwheel Galaxy, M101. In 400 years, technology has advanced almost as much as our understanding. Today, astronomers routinely scan the skies with spectacular telescopes, many of them seeing kinds of light that Galileo didn't even know existed. In the 1970s, this photographic exposure of the Pinwheel Galaxy from Kitt Peak National Observatory was one of the best of the time. Larger telescopes and advanced digital detectors have continued to improve the view over the years. Space-based observatories have brought amazing new ways of seeing the familiar objects like M101, as with these recent images from the Spitzer Space Telescope, the Chandra X-ray Observatory, and the Hubble Space Telescope.
The combined image represents 3 different parts of the spectrum, spanning X-rays, visible, and infrared light. But how do we make an image we can see using light we can't see?
The human eye is a remarkable biological instrument that detects electromagnetic radiation, or light. The eye's cone receptors come in 3 different varieties that let us independently perceive 3 different sections of the light spectrum, what we call red, green, and blue. All the other colors we recognize in the visible spectrum are just combinations of these 3. While the full spectrum of light extends far beyond what we can see, our sun is brightest right in this range. That's not surprising. Millions of years of evolution should produce eyes that take maximum advantage of what the sun provides. If humans were to evolve around a cooler, redder star, their visible light would include what we call infrared.
While they might even think of color the same way that we do, their reds, greens, and blues would be entirely different than ours. So, why not use technology to change our colors around too? Because of the way our eyes work, we can break down any color image into its red, green, and blue components. But the colors we display can come from any part of the spectrum.
For instance, this Spitzer image of the Pinwheel Galaxy draws the imagery entirely from the infrared spectrum, but presents them in human-friendly colors. We do the same thing with this Chandra image, but now we're using X-ray observations as the source. The colors we see now mean something entirely different than they did in the Spitzer image.
This is sometimes referred to as a false color image, but that makes it sound like there's something fake about it. Instead, it's better to think of these as representative colors, stand-ins for real colors that we can't see ourselves.
In contrast, we might say this Hubble view of M101 is natural color, since it represents the colors more or less the way our eye would see them, assuming we could actually see something so faint and tiny.
This new image goes even further, combining each of the previous observations into a single view. Blue features represent X-rays, while the red colors are infrared. Visible light is yellow, which itself is a combination of red and green. There isn't a formula that tells us exactly how to assign these colors. Art and aesthetics have a role to play along with the science.
We could make a slightly different choice for representing the colors in these observations. This version emphasizes different features and has a different visual impact. Some people may like this one better, even though it's showing exactly the same data.
400 years ago, all Galileo had to explore the sky was a small telescope and a big curiosity. But today, the heavens are just a few clicks away, and with a richer color palette than Galileo could have ever imagined. For the Spitzer Science Center, I'm Dr. Robert Hurt, reminding you that there's a hidden universe that, with a little digital help, everyone can see. Easily seen with the naked eye on a dark night, the Orion Nebula takes on a new dimension when seen in infrared light. It's a place of star birth, from the trapezium cluster of massive stars whose light sculpt the dust around them, to the youngest protostars buried within the densest clouds of dust. The central region of this nebula is only a small part of a vast expanse of gas and dust that is one of the largest star nurseries in our Milky Way galaxy. NASA's Spitzer Space Telescope has observed a large swath of this cloud, revealing the extensive dust structures and the myriad baby stars hidden within. Jets of material streaming out from these protostars light up as they pass through the surrounding gas clouds. In this rendering of infrared light, the jets appear as greenish arcs and filaments against the backdrop of red dust. Hubble's detailed visible light view of Orion complements Spitzer's infrared vision. When merged together, we have a more complete way of seeing this familiar object. Blue and green features trace visible hot gas within the nebula, while oranges and reds reveal the underlying infrared dust patterns. The fading light of a flaring young star has shed light on a puzzle involving crystals and comets. For the most part, the universe changes very slowly compared to, well, us. The stars appear much the same to us today as they did to our ancestors. So, it's a rare treat when astronomers actually catch a star in the act of doing something unexpected, especially when it helps solve a long-standing puzzle. The star of this special event is about 500 light-years away and known as EX Lupi. It's probably a pretty close match to what our own sun was like in its infancy about 5 billion years ago. Early in 2008, it flared dramatically in brightness due to material from its disk falling onto the central star. The star's brightness increased by a factor of 100, heating the disk far from the star. It appears that tiny dust particles far out in the disk melted slightly, or annealed. As they cooled, they took on a new crystalline structure. This is the first time astronomers have ever caught crystals in the act of forming in a circumstellar disk. So, how is it possible to detect such tiny crystals around a star that is so far away? Well, dust is a specialty of NASA's Spitzer Space Telescope. Not only has Spitzer shown that dusty disks are common around young stars, its infrared spectrograph also allows us to study their compositions. By splitting its light up into a spectrum, astronomers can look for unique features, like spectral fingerprints, that correspond to specific minerals. This first observation of EX Lupi was made in 2005 and shows the signature of silicate minerals, which are pretty typical for dust. A second spectrum of this star, taken about 3 years later in 2008, shows a subtle but remarkable change. The extra bump comes from tiny olivine crystals mixed in with the dust, crystals that weren't there before. These crystals are known as forsterite, a form of the mineral olivine. Spitzer has seen this material in many places, surrounding young brown dwarfs too small to become stars, as well as white dwarf remnants of long dead stars. It's even seen in the winds around supermassive black holes in the cores of distant galaxies. This discovery is remarkable because astronomers had never before witnessed such an ongoing chemical change in the disk around a young star. But it also solves a puzzle, not about distant stars and galaxies, but about comets right here in our own solar system. On July 4th, 2005, NASA's Deep Impact probe smashed into the comet Tempel 1. Spitzer's spectrograph observed the plume of ejected material and found the comet contained the same kind of crystalline olivine. This seemed odd because comets come from the cold recesses of the outer solar system. Crystalline olivine, however, requires high temperatures to form, presumably near the young sun. So, how did these crystals make it into comets that came from all the way out there? The forsterite forged around EX Lupi could solve the puzzle. These brilliant flare-ups in EX Lupi, which may happen every few decades, will heat up more distant parts of the disk. This would form the crystals in areas that would otherwise be too cold. If our own sun experienced similar flare-ups in its youth, which we think is the case, it could explain how forsterite ended up in comets like Tempel 1. Sometimes, a small wiggle in a spectral plot can tell a big story to the scientists who know how to read it. And sometimes, a discovery around a distant young star can tell a lot about what's happening right here in our own astronomical backyard. For the Spitzer Science Center, I'm Dr. Robert Hurt, reminding you there's a hidden universe just waiting to be discovered.